now talk about SAS, where we try to augment Dutch roll, omega and zeta. Okay? We have seen that omega d from first or 1D analysis, it is directly proportional to n beta in one dimensional, right? And n beta has Cn beta into this, because n beta is half rho v square SV Cn beta by I zz. So if I want to increase omega Dutch roll, that means I have to increase Cn beta. Remember, for longitudinal natural frequency, we have to increase the Cm alpha. So what should be the logic here? You have the airplane, and all this yawing motion, we are attributing authority to the rudder. Okay? So let's say this is, I am tapping beta, gain I am multiplying, and I am deflecting delta R proportional to beta. Right? Okay? What is happening by doing this? I am adding delta Cn yawing moment, that will be Cn delta R into delta R. So that will be equal to Cn delta R into k beta. So that is delta Cn additional. So additional Cn beta will be how much? That is delta Cn by beta, that is k Cn delta R. So this is delta Cn beta. So let us come back again here. Suppose I have got Dutch roll frequency basic. I had, let's say, WD B, and say basic. Now, with this basic, whatever the airplane has, we found the corresponding Cn beta was Cn beta basic. Now you want to increase Dutch roll frequency. Hence, Cn beta has to be increased. How much it has to be increased? For that, for approximate value, I can use the expression for omega d equal to under root of half rho v square s Cn beta by I zz. So all these values I know. From here, whatever Dutch roll nu is required, that I put on the left hand side, and for a rho v and s and I zz, I know what is the Cn beta nu required. Total, right? So I have got Cn beta is Cn beta basic plus Cn beta, which will come from SAS. That is the additional. Okay? And this is the required, or desired, or required, whatever you say. Who decides this Cn beta desired? That is linked to whatever omega d required, which we got approximately from here. Right? So now I know that delta Cn beta SAS should be equal to Cn beta desired minus Cn beta basic, and this is equal to k Cn delta R. It has come from here, right? So I can easily find out the k is Cn beta desired or required minus Cn beta basic divided by Cn delta R. So I know what value of k is required, but always remember, if k is too high, it may make the system unstable. So that is why I always say, whatever value comes, then again you have to go back to the AS4 plus BS cube plus CS square plus DS plus E equal to 0 and see where are the roots lying, right? Especially Those who will be working on control, you'll find this is done routinely, although there are shortcut way of getting some first information. Okay, so now the next question comes, if I am deflecting delta R as k beta, then what happens? Is there any other derivative that gets affected? See that in Cy, we have one term called Cy delta R into delta R. So this will now get additional effect Cy delta into k beta. Okay? So here we had Cy beta into beta. There may be Cy p into pb by 2v or 2u1, like this, blah, blah, right? So now Cy beta into beta was there. Now Cy delta into delta, so this is Cy delta into k beta. So finally you find Cy beta plus k Cy delta R into beta. So your Cy beta effectively gets modified, right? Because Cn beta has got modified, so Cy beta also gets modified. So we have to see what is the effect of this overall stability of the system. Right? This understanding is must. What is the final thing? You know from the handling quality requirement how much omega d you need to have. If it is less, you have to increase, so you have to increase Cn beta. If it is more, you have to reduce, so reduce Cn beta. So accordingly you decide what type of beta feeding you will be doing for natural frequency. Okay? Once that is done, now if you want to change the damping ratio for Dutch roll, and you know that damping ratio will be proportional to NR, and NR is proportional to CNR. What was CNR? Whatever is CMQ for longitudinal mode, CNR is for directional mode, right? That is your damping, okay? So I have to ensure that if I want to increase zeta, I need to increase CNR. If I want to decrease zeta, I have to decrease CNR in flight through SAS. So what will be the approach? Again, the approach is same. This is the aircraft. Now you will be tapping R, and again you multiply with this, and delta R you put as KR. Deflect delta R with, which is proportional to rate. And how do you measure rate? You have a rate gyro. You can measure this. So the moment you do this, how much delta Cn this will introduce? That will be Cn delta R into delta R. And this is equal to Cn delta R into KR. So this is delta Cn. So I divide delta Cn by R, RB by 2U1 to get CNR additional, that is equal to Cn delta R KR divided by RB by 2U1, right? So this RR gets cancelled, so you have 2U1 by B K into Cn delta R. So that is the additional CNR you have to generate through SAS. So it's very simple now. What is the, how do I find additional delta CNR? You know, CNR basic, which was for the aircraft. You know, CNR desired, so that you have right type of damping ratio, which you get approximately using one-dimensional analysis. And so delta CNR is nothing but CNR desired minus CNR basic. That is equal to delta CNR, and that is equal to, just now we derived 2U1B into K Cn delta R. So you can find that K in this case will be CNR desired minus CNR basic divided by Cn delta R into B by 2U1. Am I correct? So K will be equal to into B is B by 2U1. Please check yourself. Okay? And this is Cn delta R. This is K. Right? And again, as you know that, I have to fit this back to the dynamic stability exact equation and see how the roots are changing, because it will have an effect in other derivatives as well. Okay? See, I always say that if this is the value of K, which will take care of CNR, new value required, so that you have a correct damping ratio. But we should also check that this will have effect in other derivatives. For example, if I see rolling moment coefficient, CL is CLP into PB by 2U1 plus CL beta into beta plus CLR into RB by 2U1 plus CL delta R into delta R. Now check here, what is happening? We are putting delta R equal to KR, this R, the same thing, same notation, don't get confused, this is R and this is R, okay? So then check out here, it is CLR into RB by 2U1 plus CL delta R into, for delta R you write KR. So effectively what is happening? You see what is happening now? If I take, this is R is lying here, here R is lying here. So now this CLR, effective CLR is getting modified, okay? So this CLR prime will be the sum of these two, and appropriately you take B by 2U1. So what I do, I write this simply as, this is CL R into RB by 2U1 plus CL R into KR, okay? And I then write this as CLR into B by 2U1 K. I multiply this and same thing. So I can take CLR into RB by 2U1 R. R is here. There is R. So if I take RB by 2U1 from here and here, so I have RB by 2U1 and a common, I say CLR plus CLR K 2U1 by B, right? Because I have taken RB by 2, yes, correct. You can yourself also do. Please understand this. So this is the effective CLR now, sum of all this. So what has happened? Although you wanted to increase the Dutch roll frequency by giving a rate such that rudder is deflected proportional to the rate, although zeta has increased, but you have changed the value of CLR, right? So this is again a cross coupling happening. So you have to be very careful and go back to those exact solution and see where are the roots lying. Are we achieving those things which we are looking for or not? But the beginning is here. If this is correct, then rest is just mechanics. Just mechanically you can do. So I thought I will give you this insight here on this, and I request you please do it yourself. Okay? This thing you should do yourself. Thank you very much.